Swayam Prabha. Digital India. Educated India.
Good morning. So, this is probably the last class in this semester, and very quickly let us review what we had discussed in the last class. In the last class we talked about the cycloaddition reactions, right, and that was exclusively 4+2 cycloaddition reactions. And in heterocyclic chemistry there are all kinds of cycloaddition reactions, but the most popular ones are 4+2, 3+2, 2+2, 4+3 and 5+3. These are few, but there are many other higher order cycloaddition reactions. Okay, and we began with 4+2 cycloaddition reactions. Today we will begin with 3+2 cycloaddition reactions. 3+2 cycloaddition reactions. And quite often you will be hearing also a terminology called 1,3 dipolar cycloaddition reactions. Dipolar cycloaddition reactions. In fact, both are very similar. I think you all understand the meaning of 1,3 dipolar cycloaddition reactions. 1,3 dipolar cycloaddition means you have 3 different atoms, X, let us say X, Y and Z, X, Y, Z, and that means 3 atom synthon or reagent, in which the terminal atoms will have charge separations. That means one end should be negative, other end should be positive, and it could be, and the intervening bonds could be double bond, triple bond, and all kinds, double bond and triple bond. At least one double bond must be present in one of those. So, a dipole means 1,3 dipole means the charge separation takes place between the 1 and 3 atoms, and 1 and the 3rd atom, and they are also of different charges, like plus and minus, not plus plus or minus minus. And common reactions, all of you understand that this sort of molecules or this sort of things can react with olefin. Yes. And so obviously what you will find after the reaction, so you will have a kind of a 5-member ring system. So that means 3+2 cycloaddition reactions are exclusively for the 5-member reactions. And there are other reacting partners. That means if they react with triple bond, so this X and Y and then Z, and then you will have a double bonded compounds. So this methodology is a very powerful methodology, and this lecture would be sort of devoted to one of the very pioneer in this field, Rolf Weisgen. This is a German chemist. He is now more than 90 years old, and is a very pioneer. I mean, he actually throughout his life, maybe 30-40 years, he worked exclusively on the 3+2 cycloaddition reactions or the 1,3 dipolar cycloaddition reactions. And many of you probably know some of the reactions we will talk about, but one of the earliest reactions in German industry was the conversion of cyclopentene to cyclopentanone in one step. How can it be done? And again, this was due to Rolf Weisgen and a German company. What they did, they reacted with nitrous oxide. If the nitrous oxide, what happens, I think if you write the structure of nitrous oxide, it would be again a structure like this, and all of us know the structure would look like. So, that means first and third atoms are charge separated, and one is plus and other is minus, and so it is a 1,3 dipole, and that undergoes cycloaddition reactions. This is what we call the 3+2 cycloaddition reaction. And so, what you will find? You will find a pyrazole derivative. And what next? The next is just simply heating. Heating is good enough. That would rearrange, or that will shift the hydrogen. Eventually, what will get this with the loss of nitrogen, you can get the cyclohexanone, cyclopentanone. That was one of the earliest reactions, and I don't know whether this is now being used in industry or not, but this is just an example to tell you that cycloaddition reactions could be very powerful otherwise. And in heterocyclic chemistry also there are many kinds of actually 1,3 dipoles. So, some of the reactions probably you would know. Let us say if you have an ester group here and dimethyl diazomethane, or you can say diazopropane, and if you allow it to react at, let us say, 0 degree centigrade. So, what is the reaction? Diazomethane normally is again a cycloaddition reaction takes place. But so one can quickly write that this is the structure and the double bond participates in the reaction, but there is an ambiguity that nitrogen end can react on this side and carbon end can react on this side. Normally the carbon ends becomes this negative charge. So, you can say this is negative charge, and if you write this is what plus, this is minus, and so the electron flow as if comes through carbons, and so attacks this beta carbon here, and then this one goes to this. So, what you will find a 5-membered ring. This is an ester here, and this is methyl group, nitrogen, nitrogen, and nitrogen, and then you have this methyl group here, right. So, something wrong. This should be double bond. So, this sort of this is pretty well known, right. For example, nowadays one of the very popular reaction is let us say if you begin with phenyl azide, and which is equivalent to phenyl. This is nitrogen again, nitrogen, and so one can write this. This is best way to write. It's an azide here, and if it is reacted with an alkene, so electron deficient alkene. So, the electron flow again through what sort of phenyl, and it takes place, and so what you will find again a 5-membered ring. So, it is a nice reaction. That means you do not lose anything. Addition means you do not lose anything. So, we will have triazole derivative. And by now all of you know this sort of reaction is known as click reaction. So, click reaction. Then a few days ago, it is pretty popular, but I mean almost everybody knows. But you have to know what are the qualifications to be met for a reaction to be called as click reaction. What is the first criteria? It is a cycloaddition reaction. There are several criteria that to be fulfilled by a reaction to be known as click reactions, but normally click reaction is reserved for the azide and alkene or alkyne cycloaddition reactions. Okay. There are other 1,3 dipoles. For example, in fact, the compounds of this kind, all of us know. If you have compound of this kind, then again an electrodeficient system. So, sometimes room temperature, sometimes heat. In this particular example, just heat is required. So, what you will get? You will get iso-oxazole. Once again, the polarizations and attacks takes place through the carbon here, and so E, but normally this is R, and this is phenyl, and then of course you will have this isomeric problem. The isomers are often obtained, and what is the net result? This is basically again a reaction, and the substrate here is known as nitron. So, nitron cycloaddition, sometimes we call nitron cycloaddition, but these reactions, and what does it do? Essentially, if you normally the nitron cycloaddition products are broken or rather are cleaved at the nitrogen oxygen bond. So, if this is cleaved, then eventually it will give you an open chain compound, but net result, if you look at this, is the formation of a new carbon carbon bond between the carbon adjacent to this alpha adjacent to the nitrogen and the beta carbon of this acrylate. So, it is again a simplified version of CC bond formation, but we mechanistically view this as a 1,3 dipolar cycloaddition reactions. Quite interestingly, I will give you one more reaction. If you begin with benzaldehyde and then ethyl diazoacetate, and of course, this is two ice, then a reagent that would decompose diazo compounds. What is the reagent normally used for decomposition of the diazo compounds? Copper, silver, perfluoride, even copper salts also useful, cupric acetate, trifluates, all these things, but one of the finest one is dirodium tetraacetate, is one of the finest dirodium tetraacetate, or you can substitute the acetate with a longer chain acids, and just heat. Normally is toluene benzene temperature is sufficient. What you will see, the products product here is a very interesting product. It is a kettle. It is a kettle with phenyl here and the phenyl here, and phenyl here. Suppose you did not know this method, then for the preparation of this sort of kettle, what you would have done? You would have taken a diol and then benzaldehyde, and that is the conventional one. But that means, but that requires acid. But in this case, it is somewhat like a neutral reaction medium, and what is this mechanism? The mechanism goes like this. So, once it forms a new kind of a dipole, you have, if you rewrite, the structure would look like this, and if it decomposes, it forms carbene, right. So, this is a carbene, and the lone pair oxygen goes to the carbon here. So, what you will find? You will find, so CH, right, double bond, and then electron of oxygen is donated to the carbon. So, this should be plus and this should be minus and this. So, essentially you can write the resonating structure. If you resonating structure, you will find this is plus oxygen and CH, and then CO2 and this minus, right, or I mean there are all kinds. So, this is all kinds of problems there. This could be CH minus, oxygen and C plus. So, what next? And all of us can guess between all the all the three all the three, the one that would be or other. Okay, let me quickly rewrite the dipole. The dipole here is a carbon, oxygen and CH. This is plus, this is minus, and this is oh, there is problem again. Ester here. So, I mean you can write, you can rewrite also. This is C minus oxygen and this is plus and this is ester. And what next? Then you have an additional molecule of benzaldehyde. So, benzaldehyde would, that means it would react with this end and this oxygen would attack this. So, what you will find that the product would be this CH, this is what this CH, P and then oxygen and this, and in this case you have this ester. So, this is just an example of basically the 1,3 dipole. Then just very quickly. So, what are the I mean in principle what you need is an heteroatom, that means like oxygen, nitrogen, etc. you need an heteroatom, and in all cases the products you get is in a heterocyclic product. So, what are the possible 1,3 dipoles? There are so many possibilities, right? So many possibilities.
Can I please bring down that paper?
Right. So, what are the possible dipoles? That means X, Y, and Z. So, you can have all kinds of the combinations, nitrogen, 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 carbon, nitrogen, 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 carbon, nitrogen, all permutation combination you can count. But in heterocyclic chemistry, only few of them are regularly used, or I should say more popular. One of them is I think the one only today we will basically talk about. Yes.
Sir, how that resonance structure obtained?
Or how this resonance structure obtained? Okay, maybe this is it a trivial question or a tough question? Joy? Then I will take it up, otherwise I will not take it up. Okay, you can just do this little bit, so that then it becomes CH, right? Okay, so this fine. So, it becomes CH minus this is right. So, it is a good question for BSc resonance. Okay. Any case, so 1,3 dipole is this, and so you can have all kinds of combinations. Okay. And just very quickly I will just summarize, and only I will take up today only two of them. I think some two means one is known as I think we have already talked about azides, right? Azides means, so you have this nitrogen again, that means all the atoms are nitrogen, and this is plus and this is minus. So, what are the comments? I think we have already known that this should be known as the okay. We are not going to talk about today. What we will be talking about today is azomethane ylide. It is a very popular dipole. It is a very popular dipole, and how does it look? Azomethane ylide. The name tells you, in this case azo is a somewhat like a misnomer, right? Many of it. Diazonium salt, it has 2 nitrogen. Azo compounds has how many nitrogen? Azo compounds? You see, azo is 1, azo is 2 again, and diazo also 2. So, all there is a little difference in the nomenclatures. When you say azo, this is a classical name. So, azo means actually it has a nitrogen here, double bonded nitrogen, and methane means CH. So, that means it will have a CH, and ylide means you will have one more sort of a carbon. So, that means it is a negative charge, and this one is positively charged. So, this is called azomethane halide. Okay. And then there are carbonyl halide. Carbonyl halide, again instead of the nitrogen, what you will have? You will have something like this, minus and oxygen plus. So, these are all these carbonyl halides, and you have already known, say, diazo alkanes. This constitute another category of this thing. Then I will not write that, I think all of us know. Okay, how is that? Fine. And then there is we have already talked about nitrons. Nitrons means how do I write nitrons? It's nitrogen, oxygen, this plus double bond C here, and mind it, this nitrogen must contain another carbon, or which sometimes the carbon can be substituted by nitrogen, like aldehydes and ketone. The name is derived from ketones, nitrons, and all these things. Okay. Then this is another very popular one, nitrile oxides. Nitrile oxides means, all of us know, nitrile is essentially the cyanides, and if you just oxidize at nitrogen, so it becomes the nitrogen plus and oxygen minus. Then there are many other things, nitronates and all kinds of things. Nitronates, then we have, there are many. Okay. So, today we will just take up only this one, azomethane halide is very popular, and the carbonyl halides, and rest we will not talk about today. Maybe if time permits, we will do little bit of an exercise on these sort of things. So, in discussing about these azomethane halide, what is the first thing what you should know about? The first thing we should know about a little bit of the history, maybe, how this sort of concept was derived, or and how it is used, and then how it was developed into a synthetic chemistry. Okay. One of the earliest reaction in the chemical literature was this hydrogen derivative transforming to a cyclic compound with in the presence of lead tetraacetate. It's a lead tetraacetate. If you treat with lead tetraacetate and methanol, what you will get? You will get a 5-membered diazo compound, or say pyrazole, 5-membered oxopyrazole, and like this. So, you have methyl group, and then on side you have this. So, this was known. Okay. And you can guess, I think the mechanistically, if you look at this lone pair goes to this nitrogen, the double bond shifts, hydrogen goes to the lead, eventually the cycloaddition takes place. This is one of the very early examples. And if you hit this molecule here at 70 degree centigrade, and one can guess, and what is the product. Someone probably would argue that okay, this compound will have a diradical structure with loss of nitrogen, but the mechanistic organic chemist, they suggested that this compound has a dipolar structure, like this. Okay. So, dipolar structure, and or you can write like this. As if this lone pair goes here, nitrogen and this. So, you have again this is known as what, or this intermediate is known as carbonyl halide. So, it looks like you have a carbonyl plus, and then corresponding carbon is negative charge, these sort of things, and this has been well proven. Well proven means if you carry out the reaction in presence of acetone, what you will find, the product that would be forming again a 5-membered ring, 5-membered ring with 2 oxygen here and this OMe and this methyl and this. So, in other words, this carbon this negative charge goes to the carbon and then oxygen attacks this carbon here. So, eventually you get then 1,3-dioxylants are okay. Now, one could have argued okay, the intermediate is radical etc., but this sort of intermediate has been also trapped by chloroform. So, one can guess what would be the product here. All of us know the chloroform does not undergo radical kind of reactions very easily. So, the way it has been what has been found that this negative charge picks up this hydrogen and then CCl3 minus goes to the other carbon, and that means the product that would be formed here is this is CCl3 and then oxygen of here and then you have this 2 methyl group and the chloroform hydrogen is picked up. This is one of these earliest example. What does it I mean by giving this example, what I meant to say that this sort of elite structure which was originally proposed in very old literature could be short living or existing or it could be a reality, With this then I mean people have tried many other examples. For example, very nice example, let us say I think whether we can predict any reactions from a compound of this kind where you have few substituent around an epoxy ring system and this is an aryl here. Suppose we did not know anything about this chemistry of the epoxide, the special chemistry of the epoxide, and if we heat such a compound, what do we expect? Normally CC bond breaking. Why suddenly epoxides are not known to undergo CC bond formations breakage? Okay. But because of the substituents, I think this epoxide they undergo electrocyclic ring opening, 4-electron electrocyclic ring opening. And if you look at the end rather intermediate, what you will find, this is oxygen now, positive charge here, and this is very uncommon among the epoxides, but when you have heavily substituted epoxide, you will find this epoxide undergoes ring opening. But how do we know? So, if suppose simply if you heat it and then cool it, you go back to the starting material. So, but we cannot prove, right? But if the only proof which is somewhat indirect is this: if you can carry out the reaction in the presence of let us say presence of an olefin, electron rich olefin of this kind, that means ethyl vinyl ether, and the way I have written, one can quickly understand what should be the product, because this oxygen lone pair drives this lone pair to this end, and the negative charge goes to this one. So, eventually what you will find? You will find a furan derivative with ethoxy here, then CN and this phenyl, and on this side you will have an aryl group, and the yield of the reaction in this particular case is 100%, and one isomer. Of course, this is somewhat I mean unpredictable, but you got one isomer. So, that means the earlier example was an historical example, or okay. For a long time this chemistry was not explored because of the non availability of the methods by which one can produce the carbonyl elite. Now, this is one of the finest way of getting into the carbonyl. Epoxide can be ring opened to the carbonyl halide, and then subsequently these halide can be trapped by various olefinic substrates, and this has been generalized by many other cases. Like one of the cases could be here in heavily substituted again in epoxide, an internal double bond, that substituent like acrylate part. Then you have this vinyl silane, and it requires little high temperature 145 degree centigrade, and if you mix up with, or rather if you mix with acetylene dicarboxylate. So, I mean, as usual what you would expect, you would expect again a ring opening of the epoxide. The polarization takes place in this direction probably because of this electron withdrawing group. So, I think I will just write only the part of it. So, what you will see, this becomes positive end and this become negative end, and then you have this ester part. Okay, so this silicon here and this. Then one can I mean all of you can write the structure would be, the final structure would be again a furan derivative. Is a furan derivative here, and all these substituents are as it is. Ignore the stereochemistry at the moment because there is no specificity here, and so this is R. Sorry, okay, on and R. Okay, so it has to just take the okay, this is let us say E, and then you have this vinyl silyl groups. So, these two examples tells you that this sort of reactions are quite general, and more interestingly there is one more example where you will have heavily substituted epoxide, methyl and phenyl, and as the substituents, and this base, then if you photolyze at 254 nanometer, you can get also these carbonyl halides, and then it can be trapped with these cyano compounds, and the corresponding furan derivative is obtained. Okay. So, it is a very general reaction. What else can you do? What else can you do? There is another interesting way of producing these carbonyl halides. This example could be again from the decomposition of the diazo compounds. Like we have seen decomposition in one of these previous examples, we have seen that decomposition of the diazo compounds. So, that is a very general reaction. I will just give you one simple synthesis of substituted furan, which starts from a malonate derivative, where you will have the one end is this amide, other end is the ester. Then do a typical reaction of this again. So, it is a new kind of a furan synthesis, let us say. So, we will begin with new furan synthesis via carbonyl halide. Okay. So, let us see whether you can predict the product. One of the reactants is tosyl azide, and the base is used is a DBU. Anybody can guess what is the product? Azide transfer. It is an azide transfer reaction. So, this is double bond CaO Me, and then nitrogen up here, and the negative charge goes to the nitrogen, and tosyl amide is produced. Okay. Tosyl amide produced. So, what you will find This is basically the corresponding diazo compound. So, it is not azide transfer, it is a diazo transfer. This should be known as, azide means 3 carbon nitrogen. So, it should be known as diazo transfer. Okay, this is a very useful method though. One of the Indian scientists from Hyderabad actually described this one, but now we have all kinds of the variations. Quite interestingly, now this popular reagent, so, dirhodium tetraacetate. Tetraacetate, and normally it is toluener benzene and heat. So, what do you expect? Oh, sorry, I think I made a mistake here. I made a mistake. Actually, it is not the malonate. It should be in sort of an urea derivative. So, you have one more carbonyl up here. One more carbonyl up here. Okay. So, if you heat it, obviously, by now we know that it forms a carbene. So, it is a carbene here, then double bond, and you have a nitrogen up here. So, what next? I think lone pair goes to form the carbonyl imide. So, nitrogen and then the ester here, carbonyl ylide means oxygen plus and this carbon minus, and the substituent here is methyl group. And this sort of compound, once again, if you react with the alkynes, electron deficient alkyne, electron deficient alkyne, methyl here and CO2 Me. So, all of you can write, the product would be a bicyclic compound. So, carbonyl, then you have these 2 ester groups and ester groups here, and then you have this nitrogen and this nitrogen and this, and you have this. Okay. So, it is a bicyclic compound. Right, understood. So, what next? If you recall, the title was furan synthesis by carbonyl ylide formation, okay, via carbonyl ylide. So, and if actually retro Diels-Alder takes place thereafter. So, what is the product? Product would be, it is a furan derivative with the 2 ester groups here at 2, 3 and 4 positions, and the 2 position is occupied by dimethyl amino group. And what is the loss? The loss is the molecule that is being lost, methyl isocyanate. It is a very methyl isocyanate. So, now this reaction, let us say one more example probably I will give you, whether see whether you can write the structure of the product. This is from an oxazoline derivative. So, and the substituents are the esters, and here I think I will straight away write it is again a diazo compound. It is a diazo compound. Now, as usual, this dirhodium tetraacetate, this requires little low temperature 1,2 dichloroethane, which has a boiling point around 80 degree centigrade. Okay. So, I think all of you can guess what could be if this reaction is trapped with phenylmaleimide. So, what should be the product? What should be the product? In fact, the product that is formed here, I will straight away write the product is a benzenoid. No, that means this carbonyl halide is being used for the formation of a benzenoid, not the heterocycle, but the diazo compound, the carbonyl halide actually forms from a heterocycle. Okay. And so, this is ester group here, this is OMe, and the other portion is the corresponding dienophile. So, mechanistically, as once again this is sort of like a repetition. So, you will have nitrogen, then oxygen here on this side. Now, after this formation of the carbene, it will form the carbonyl halide of this kind, and here you will have the methoxy. So, this methoxy is retained, this ester is retained, okay. And if you have then Diels solder, so undergoes thermal reaction. So, what you will find, this will be this as a typical cycloaddition reactions, and this is OMe, then this is your oxazole part, and then you have this ester here. And what next? I think again thermal loss of water. So, you will have this, and then eventually we will have one more hydrogen that will undergo thermal isomerizations to this product. So, giving all these examples, basically we are trying to tell you that this sort of carbonyl halide reactions are pretty useful reactions. Okay. What is the other way of having the cycloaddition done? I think the one next most important that we will be talking about is azomethane halide. We have already told you how to write azomethane halide. Azo in this case it is basically an unsaturated nitrogen, methane means this, and then you have the halide means you have to have a negative charge and this is positive charge. Okay. Once again this sort of chemistry was not known for a long time, but when people came up with the methods by which they can be easily be produced, then these reactions became very popular. In our country, Ganesh Pandey has been very pioneer in this area. Okay. The one of these ways to produce this sort of intermediate, how to produce was to have the silyl compounds. So, with a silyl group adjacent to nitrogen, this was the minimum requirement, and then you if you look at the structure here, you have to produce a double bond. So, that means you have to have a good leaving group, but many of you know many of the leaving groups adjacent to nitrogen are not viable. Having a leaving group close to nitrogen is not viable. For example, if you have an OH here, it is not very stable because of the lone pair of the nitrogen. So, you have to have a leaving group which should be poorer than OH and amines and etc. Okay. And but then it should be livable, or so rather I should say it should be departing this group substrate. So, in this case let us say the one that was suggested was cyano. So, and the other portion is of course this is a protecting group here. Now, if you treat this with a fluoride, all of us know fluoride would attack at the silicon. So, it forms a carbon ion, fine, but at the same time you have to have a I mean driving force for releasing this cyano group. So, how do you do? So, you have to have an electrophilic kind of thing that would attract the cyano, some special affinity to which one? Silver, right. So, in fact, this was done with silver fluoride. So, silver fluoride. So, if you do so, that means one can quickly make this one, this derivative. So, this is actually azomethane derivative. There are other methods. I think I will not maybe I will give you one more example. One more example. Let us say there are other way of in fact, instead of this cyano, you can also have OR, alkoxy. That means a group poorer than the OH groups, etc. So, alkoxy is, all of you know, is under and that means cyano can be replaced by alkoxide, and there is another way of making it. You can have two silicons around this nitrogen, and that requires, however, say photolytic reactions. DCN, dicyano, I forgot, naphthalene, right, dicyano-naphthalene, 1,4-dicyano-naphthalene, and then light. So, you can generate again this sort of dipoles, 1,3 dipoles, so negative and positive. See, this is one way of, that means silyl derivatives of the corresponding amine compounds can be desilylated to produce this azomethane halide. And then there is another sort of way of doing it. I think the best thing would be I mean just imines or iminium salts, for example. If you have a substrate of this kind, right, then if you put an electron withdrawing group here, withdrawing group here, let us say an ester group, and then of course ester group, then one can from here the ammonium salt, let us say ammonium kind of salt here, then automatically the alpha position becomes a little more susceptible to hydrogen abstraction, and so hydrogen now in presence of a base you can produce. This is one of the finest and quickest way of doing it. This is hydrogen and R plus and this. So, you will have a nice azomethane halide. This is one of the I mean that means and imine formations, all of you know, is very simple. Imine formation is very simple from carbonyl compounds and the amine. So, this part looks like a amino acid and the other part is the aldehyde. And I will just illustrate this azomethane halide formation by a synthesis of a natural products called lamellarine H. The molecule looks, I think you have seen it before, it is a pyrrole derivative. It is a pyrrole derivative, it is a tetrasubstituted and pyrrole derivative, and the molecule would look like a real big molecule. It is a biologically active molecule, and these, and then you have OH of here, OH, this is basically here and there OH, and then you have so many OH groups here. Okay. This is the target. If you recall, in one of these previous classes we talked about the synthesis of this kind of molecule by application of Suzuki coupling. You start with a pyrrole derivative and go on putting these aryl groups here. But if you see, look at the synthesis we will be describing now, it is much more convenient, and looks little interesting in the sense that the formation of this this spiral ring by cycloaddition is pretty very easy, you do not need any sophisticated method. The first thing what is done, let us say I think in brief I will write AR means one of those phenyl groups. You begin with an acetylenic compound, and then with an aldehyde, the and here and the methoxy here, and this let us say again a methoxy for example. First this one is converted to a phenol, protect on the other side you will have OR, OMe, and this is OMe. Okay. And how do you do it? I think this is a undergraduate chemistry, right? Santanu, let us hear from you. Dakin reaction. Dakin reaction requires an OH group, right? Adjacent OH group. It is an undergraduate problem though, very interesting problem.
The reagent for Dakin solution is H2O2 and for sodium hydroxide.
H2O2 and N2. Okay, other than H2O2 and N2, what else can you do? Okay, let us say in this case the first one was MCPBA. What does it do? MCPBA actually converts this formyl group into formate. That means aryl group migrating to the oxygen. So, what you will see here, no, it is not the Dakin reactions. Dakin reaction possible, but yes, but Dakin reactions normally yields are not that great. See, if you have an aldehyde, yes, that is what I am telling you. If you have an OH group, that is very easy. This OH group is very easy. See, the Dakin reaction itself.
So this is condition for biochemical oxidation.
It's biochemical oxidation. It's a plain biochemical oxidation, aryl group migrating to the oxygen. So, what you will find here, I mean, let us say A prime. So, what that is it. That means insertion of an oxygen between the aryl group and the formyl group. It's a basic. Then, what you do? You have to just release this to OH group. How do you do that? Hydrolysis, yes, hydrolysis, that is obvious. It's the format you convert this, but the preferred method that at this moment you have to think about other methods also, not classical OH, etc., etc. Okay, the preferred method is simply ammonia and what else? Methanol. Okay, that is basically transesterification. So, then this is converted into OH and once again an ester here, and so you take iodoacetic acid. So, from iodoacetic acid you corresponding the ester is, and how do you do? It is not very trivial though. You have to use DCC here, DCC and DMAP. Okay. Next you do, you take a dihydroisoquinolidine, and this oxygen of and all these things, whatever then this solvent. So, that would lead to the quaternization, and and nitrogen here, and this is this acetic acid part, and this is this one, and then this. So, you get the quaternization here. So, what is then if you see, that is the triple bond here, and that is the aryl part here, and the rest as it is, here and there you have this oxygen here, all these things. So, what we will see that now this is an iminium salt, and we have an hydrogen here which should be abstractable. In the presence of a base which is known as Hunic base, isopropyl, so basically it is a trialkene amine base. This gets converted into the dipole, 1,3 dipole. So, what we will have now, this is negative charge and this is negative the positive charge here. I think I will write this way, otherwise this is then carbonyl, maybe now you will have this, this one, and then you have this triple bond, right, and this is Ar, and then you have all kinds of this oxygen here and here, So, this will undergo now, you see here the triple bond is not a very activated one, neither does it have any electron withdrawing groups, nor it is otherwise activated. So, this under the condition this reaction takes place and it forms the pyrrole ring, So, the pyrrole ring, then of course, if you write the pyrrole ring, then you will have a product without the double bond up here. So, you treat this with DDQ, dichlorodicyanoquinone, benzoquinone, and that would aromatize this quinolyl ring, and then subsequently you treat this with boron trichloride, is a reagent known for demethylations, O demethylations. So, O demethylation. So, you get to the compound called lamerarine. So, this I mean very quickly I have said about this one, but essentially is a azomethane halide, and there are two kinds. One is that silicon substituted substrate for the synthesis, and the other one, this one is an iminium salt, which can be converted into the azomethane halide. Okay, and mind it, this does not require any activated alkynes. So, similarly, this sort of reactions also is very useful for unactivated alkene, provided it is present within the molecule. That means, if the reaction is an intermolecular one, this 1,3 dipole is nicely reacts with an unactivated, ordinary olefins means otherwise unactivated. Okay. And maybe I think we have run out of time, and you can try to work out one of these problems at home. The problem is like this. This is again from this recent literature. If you mix up with proline heated with benzaldehyde in the presence of nitromethane, you get nice CC bond formation, and see whether you can work out the mechanism.